For decades, computational complexity has treated mathematical proof as an inscription. In the classical baseline, known as NP, a proof is a static string of text, a certificate, that a deterministic algorithm reads and verifies. The checking is pure syntactic logic. But if you replace that classical checking algorithm with a quantum circuit, the entire concept of verification fractures. In the quantum regime, you can no longer simply read a proof from top to bottom. The evidence itself must be a physical state in Hilbert space, subject to the constraints of quantum mechanics. It carries superposition, interference, and uncertainty. Verification now depends on how that state behaves under specific measurements. Checking a claim inherits the material constraints of quantum information. It is an operational procedure limited by disturbance, the impossibility of cloning, and the fundamental bounds of uncertainty. This dynamic is formalized in the class QMA, or quantum Merlin Arthur. QMA is the quantum descendant of NP. It requires a uniform, polynomial-size family of quantum circuits tasked with checking a provided quantum state, yielding an acceptance probability bounded strictly away from random chance. This diagram outlines the anatomy of a QMA verifier. There is a temptation to think of the input here, the density matrix rho, as an ultra-compressed hard drive storing exponentially many classical strings in parallel. That is mathematically incorrect. The verifier's circuit doesn't read parallel bits. It applies unitary gates to create interference among amplitudes, and then it measures the output. That measurement extracts a Born rule probability, the trace of the acceptance operator applied to rho, and in doing so collapses the superposition. The evidence is actively consumed by the act of inspecting it. This introduces a massive structural hurdle known as the No-Cloning Theorem. Because you cannot make a universal copy of an unknown quantum state, the verifier cannot duplicate the witness to run independent, repeated tests to double-check its work. In classical software, if you want higher confidence, you just run the verification loop again. Amplifying your certainty with quantum evidence requires designing specific circuits that coherently reuse the exact same quantum state, carefully extracting information without completely destroying the original mathematical structure. To see how physical this gets, we look at the canonical problem of QMA. In classical complexity, Stephen Cook and Leonid Levin proved that any NP problem can be mapped onto a Boolean satisfiability puzzle. The exact quantum analog to that theorem is the K-local Hamiltonian problem. A Boolean formula is a sum of local logical constraints. A local Hamiltonian translates these into quantum constraints, manifesting as local energy penalties. A zero-error assignment becomes a minimal energy state. Kitaev's clock construction entangles an entire computational timeline into a single static history state. Under this encoding, checking a proof is mathematically identical to solving an eigenvalue problem. The verifier calculates whether the ground state energy of this Hamiltonian system sits below a certain threshold, meaning the proof is valid, or above a higher threshold, meaning it is false. This perfectly maps onto early ideas posed by physicist Richard Feynman, who suggested that the complexity of nature could only be simulated by a machine operating natively on quantum rules. The local Hamiltonian problem closes that loop. It demonstrates that verifying a mathematical theorem and estimating the low-energy behavior of a physical material are structurally the exact same computational object. Treating proof as a physical state creates strict theoretical blind spots. In classical computer science, the PCP theorem proved that a verifier can robustly spot-check a few random bits of a long proof to determine if the whole thing is globally valid. A quantum version of the PCP theorem remains unproven because of entanglement. Quantum states can be intensely entangled in such a way that if you measure them locally, they look entirely consistent, perfectly hiding massive mathematical errors on a global scale. To map this obstruction, researchers proved the NLTS theorem, no low-energy trivial states. It confirms the existence of local Hamiltonians, where every possible low-energy state is globally entangled, so deeply correlated they cannot be prepared or disconnected by localized quantum circuits. Entanglement shatters the intuition of classical spot-checking. You cannot reliably use local-to-global reasoning when inspecting a highly correlated physical proof. Single-prover systems like QMA are bounded by the limits of local energy testing. If we introduce interaction, where a verifier interrogates a single prover back and forth with quantum messages, we define the class QIP. This interaction maps perfectly to classical p-space bounds. The verification power scales, but it remains finite. Complexity shifts when we introduce multiple provers in the MIP star model. Two isolated provers receive questions while sharing a pre-existing entangled state. This allows verification to reach recursively enumerable languages, or RE, including famously undecidable problems like the halting problem. This leap occurs because entanglement allows the provers to coordinate using strategies that have no finite representation. The verifier uses non-local games to self-test the provers, essentially forcing them to demonstrate that they are measuring an infinite-dimensional operator algebra. Even though the verifier only sees finite classical answers, those answers certify the presence of an unbounded mathematical structure. When proof is distributed across entangled systems, the reach of the verification system is determined by the scale of the entanglement available to the provers. This pushes the boundary of what can be proven far beyond decidable computation. All of this abstraction crashes into reality when we look at the applied frontier, how a classical human user verifies the output of a quantum cloud computer. If the machine runs a process too complex for a classical computer to simulate, the human cannot simply rerun the math to check it. Computer scientist Urmila Mahadev designed a protocol for exactly this scenario. Since the classical verifier is computationally weaker than the quantum device, the verifier uses post-quantum cryptographic trapdoors, specifically learning with errors algorithms, to corner the quantum prover into predictable, testable behavior without needing to process the underlying computation. In this engineering context, the definition of a quantum proof pivots entirely. It stops referring to a witness state made of quantum information and instead refers to a classical verification protocol built to survive attacks from a quantum computer. This adversarial shift is driving modern cryptographic standardization. Institutions are finalizing lattice-based signatures and hash-based key encapsulations to secure our classical verification systems against the specific threat of quantum hardware running Shor's algorithm. We have to be precise with our terminology. Quantum proof in software engineering refers to defending classical models against disruption. That is functionally distinct from the complexity class QMA, where the mathematical evidence itself is a tangible quantum object. This animated taxonomy shows how the theoretical map of computer science has been reorganized by physics. We start with NP, verifying strings of text. We expand to QMA, checking quantum states. We move to QIP, allowing quantum interaction. And we reach MIP star, exploiting infinite entangled correlations. These boundaries are drawn by altering physical parameters. The witness creates QMA, the dialogue creates QIP, and shared correlation pushes us to MIP star. This physicalization does not abandon the rigor of mathematical proof. The standard of absolute truth remains intact, but that truth is now inextricably tied to the laws of thermodynamics, superposition, and non-locality. A quantum proof makes mathematical evidence operational. It is no longer an abstract derivation, but a physical resource, a state or correlation, that must obey the literal laws of quantum information to remain convincing.